Okay, it's live. Well, I think we'll give everybody a few minutes to join in, and then we'll start.
Do we have a link?
Yes, I think it's going to be shared soon.
Ooh, nice. Yeah. Okay, let me cast this.
Forja, let me know when you make the announcement.
Where's the link?
In Telegram.
It's there? Okay, nice. Just a second, just copy pasting it. Pasting it. Okay, announcement done.
Okay.
I'll do it on Twitter as well, but on Discord is live.
Great. Let's wait for people to join and
Okay, I'll retweet the one.
okay. I see people are joining. In any case, everybody will be able to look at this in recording. We have to thank our Optimism friends for hosting us on their platform today. And yeah, we'll be doing a quick code walkthrough for the new fault proofs. And Kelvin here from the Optimism Collective is going to do that for us. If anybody has any questions, feel free to address them in the YouTube chat. And we have Sven here, also known in the security realm as Shogoki, that is going to read your questions and ask them to Kelvin as they appear. So feel free to do that as much as possible. And I guess we'll give the mic to Kelvin, and let's hear him.
Sweet. Okay. Hello, everybody. Whether you're here live or in the recording, hopefully this will be generally useful to everybody. Cool. So, yeah, we are here today because we are finally doing our first big Sherlock competition about the new OP Stack fault proof code. So if you don't know, fault proofs are a system for basically proving, whether a claim about the state of, or really the result of some computation is actually correct or not. There's two main ways that people do these kind of proofs. There's either fault proofs or ZK proofs. You might already know what ZK proofs are, but I'm going to be talking mostly about fault proofs. And fault proofs are an interactive way of proving something sort of counterfactually, where the assumption is that something is valid until proven otherwise. And if you want to prove that, then you can do this big old back and forth thing where we determine who is correct and who is not. So, okay, so fault proofs, very important stuff. This is a big step in moving towards a future where layer 2s can basically be secured entirely through these fault proofs rather than having some sort of security council or governance, multi-sig thing that can upgrade these systems instantly. So getting the first fault proof out the door is a big step there, and you will see that we have laid the groundwork for future fault proofs as well. All right, so really quickly, before I do anything, I want to sort of explain what's changing. So I'm going to start by sharing my screen a little bit here and describe what the system looks like today. This is the code that you will see on OP mainnet today, or on Base, or whatever, any of these OP stack chains. I'm going to show you what the system looks like today. And then we're going to switch over, and I'm going to show you what the system is going to be looking like, ideally, once this fault-proof code goes live. Once we get through that, I'm going to sort of explain at a high level what these different contracts are supposed to be doing, and then we'll get into actual code so you can understand how we achieve that. So let's get my screen up on the screen, and I'll start walking you through. Oh boy. Okay. All right. So let's start here. I assume everyone can see this. Someone will tell me if they can't. Oh, sorry, this is the new version. Let's start here. So, okay, this diagram here shows at a high level what is going on today in the OP stack for the L1 bridge contracts. There is just for context, this diagram comes from an info book, an audit info book that we have created. So you can look at this diagram later for yourself if you want to. We'll share the link to that at some point, but it's also in the contest Q&A. So if you want to look at this diagram more carefully for yourself, you can always go and do that. But let's just quickly run through what's going on. And specifically here, we've highlighted these green areas here. These are the things that are changing with the system. But you can see from a high level, a lot of this stuff is going to stay the same. But at a high level, basically what usually happens, users are interacting with these bridge contracts. That's generally what's going on. Whether that's the ERC20 bridge or the ERC721 bridge, right, the NFT bridge, these bridge contracts, in order to function, need to be able to send messages between the layer 1 and the layer 2. And the way that they do that is that they go through this high-level contract called the L1 cross-domain messenger. And this high-level contract, you can kind of imagine this like a stack on top of a low-level message passing system. And this high-level thing is responsible for user conveniences like the ability to replay messages, the ability to, I don't know, there's a bunch of different things in here that's just quite nice, but this is a sort of a user land level thing. This contract here, the L1 cross-domain messenger, interacts with the low-level message passing system. This is sort of the bare metal message passing system called the Optimism portal. And the Optimism portal is really the thing that is changing with this proposed upgrade. So what does the Optimism portal do today? How does this work? Well, for deposits are not really changing in this case. This is deposits, or the sort of the term that we use for messages that are being sent from the layer 1 to the layer 2. And that direction, that messaging direction, is not impacted by the fault proof. So that doesn't really change very much. What is being impacted by the fault proof is the reverse direction. It's the direction where you're sending messages from the layer 2 to the layer 1. And the reason for that is because of how you prove that such a message was actually sent. So when someone sends a message from the layer 2 to the layer 1, what they're doing is they're basically storing some message in the state of the layer 2. Then you later have to prove to the layer 1 that your message was actually stored in the state of the layer 2. So we already know how to do state proofs, right? If you are aware, there's the state of the Ethereum is stored in this structure called the Merkle-Patricia trie, and the Merkle-Patricia trie has the ability to allow users to prove things about the state of the try. So I can prove that, for instance, the value of a specific storage slot is X. And that's essentially what I'm doing in the Optimism portal. I'm proving that within the state of the layer 2, I have stored the hash of my message. So we know how to prove in the state, but now the question is, how does the layer 1 know what the valid state actually is? Because the layer 1 does not run a layer 2 node, so it can't compute the state of the layer 2 for itself. Instead, in order to figure out what the state of the layer 2 is, you have to go to some mechanism, and this is the mechanism that we are replacing with the introduction of fault proofs. So the way that this works today is that there's a contract called the L2 output oracle, and there's a special address. There's a permissioned address called the proposer that is allowed to basically say, hey, this is what the state of the layer 2 is at this moment. Then there's another address called the challenger, and it's allowed to, within a certain amount of time, say, actually, that was not the state of the layer 2. So this works for the most part, as long as you basically trust at least the challenger to always come in here and guarantee that it's never going to allow invalid proposals to be added to the L2 output oracle. This is okay, right? If you trust the challenger, then the proposals in here are always going to be valid, and so users are going to be able to prove that their message was actually included. But obviously, the issue with this is we have to trust the challenger, and we don't want a system where you have to trust this actor within the system. So we want to fix that, and this problem of the L2 output oracle requiring a permissioned challenger is fundamentally the problem that we are solving with fault proofs. So now I'm going to switch over to fault proofs, and we're going to see how things have changed. Before I do that, I want to confirm that everything is going correctly. Can someone on the stream just give me a vocal yes that my screen is still being shared correctly? I'm just I can't share my own screen without.
We can see it.
Okay. All right, great. All right, perfect. Sorry, I can't look at the stream right now without creating that infinite window, which is very disturbing to me. So, okay. All right, so what is changing? Well, first thing I want to note is that all of this stuff, the L1 standard bridge, the ERC 721 bridge, the L1 cross-domain messenger, all of this stays exactly the same. This does not change. And that's very important because this is the high-level interface. These are the high-level interfaces that users are interacting with. It's only the low-level message passing mechanism that's actually changing within this system. So that's very important just when you think about how to look at these contracts. Okay, so what is changing? Well, we're changing the Optimism portal, and specifically, we're changing the Optimism portal so that it no longer looks at this trusted L2 output oracle. So if it's not looking at the trusted L2 output oracle to figure out what the state of the L2 is, what is it looking at? Well, the way that you can now propose the state of the L2 is to go through this contract called the dispute game factory. And essentially the dispute game factory creates instances of these contracts called fault dispute games. So a fault dispute game is a contract whose entire job is to determine whether or not a claim, a proposal about what the state of the layer 2 is valid or invalid. That's its entire job. So any user can go to the dispute game factory and they can create a new fault dispute game for a claim, right? So I can say, I claim that the state of OP mainnet at block 1 million is XYZ. and that takes the form of a hash. And I put up a bond against that claim, and a fault dispute game contract gets created. Now, this fault dispute game contract has logic in it that allows other parties to come in permissionlessly and counter your claim. So they'll say, actually, I don't think that that is actually the state of OP mainnet at block 1 million. And here's where I disagree with you, right? So the fault dispute game has a whole process. And in this process, users are going to go back and forth and back and forth and back and forth, essentially over the course of 7 days, over the course of this dispute window. And at the end of that process, somebody is going to be determined or going to be crowned the winner, right? Either the person who originally made the claim is going to be the winner, or the people who have challenged that claim are going to be assigned the winner. And then the winners basically get a bunch of bonds from the losers. So the point of this whole process is now that anybody can create claims about the state of the layer 2. Anybody else can challenge those claims. And the goal is that we eventually want to have this end state where we are 100%, 1,000,000% confident that these games are going to resolve correctly, and that if you create a valid claim, it's going to be marked as valid. If you create an invalid claim, it's going to be marked as invalid. And in that way, users can use those claims to prove their withdrawals, just like they previously would have used the claims that came out of the L2 output oracle to prove withdrawals, and then finalize those withdrawals and execute them on the layer 1. So that is the high-level idea of the system, is a permissionless mechanism for people to create claims and challenge those claims, rather than having claims being created only by one permissioned address and only challengeable by one permissioned address. All right. So now I'm going to start talking a little bit about where things are, sort of what the risks are and what it is that we're really trying to establish with this contest. So I think the first clearest risk within this whole system is that the fault dispute game contract is quite complicated. The fault dispute game contract, the resolution logic, the logic that basically determines whether a claim is valid or invalid, is quite complicated. And it's going to take time to get complete confidence in the correctness of that resolution logic. So because of that, what we've done is we've added fail safes into the system, where we know that it's possible that the fault dispute game logic could resolve incorrectly. It could say that a given proposal is valid when it should be invalid, or invalid when it should be valid. If the proposal is valid when it should be invalid, that could let a user prove and finalize a withdrawal that is not actually a real withdrawal, which would be a safety issue. And if a proposal could be shown to be invalid when it's actually valid, then that could create a situation where a user cannot execute a withdrawal that they should be able to execute, which is a liveness issue. So because of the possibility for this kind of issue, we've added a number of different fail-safes. The first sort of critical fail-safe is that the Optimism portal includes an error gap in it. And the idea of that is that after the fault dispute game resolves, there's a period of time within the Optimism portal where that fault dispute game has resolved, but it can't yet be used to finalize a withdrawal. So during that period of time, we have an entity called the Guardian, and this is essentially the Security Council. And the Guardian is allowed to either blacklist specific dispute games that have resolved incorrectly, or change the respected game type, which is basically saying this entire class of dispute game, this entire implementation is invalid, and we're going to switch to a different implementation. And so this is a safety mechanism that basically means that if this error gap window is maintained, that even if the fault dispute game resolves incorrectly, the guardian should be able to still keep the system safe within a certain amount of time. That's the first big window where we have fallbacks. The second area where we have fallbacks is in the bonds that are stored within the fault dispute game. The logic that involves resolving the fault dispute game is also the logic that distributes bonds between the different participants. And it's possible that there are there's quite a large amount of ETH in the form of bonds in the fault dispute game. And depending on how much ETH that is, it could be very dangerous if the fault dispute game resolves incorrectly. So the fault dispute game restores its bonds in a contract called delayed WETH, which basically enforces a withdrawal delay on bonds. And the point of this withdrawal delay is then that you can have monitoring within the delayed WETH contract within the fault dispute game. And if the fault dispute game distributes bonds incorrectly, then it can't actually get those bonds out for a certain amount of time. And it would be possible for monitoring to catch that issue and essentially prevent the fault dispute game from accessing those bonds. So that's the high-level mechanism of all of this. That's basically the TLDR of all the big system contracts within this contest. And our goal at a high level is to really make sure, first and foremost, within this contest, that the Optimism portal functions correctly. And so that there's a number of important invariants about the Optimism portal that we need to maintain. Obviously, the first most important invariant is that it shouldn't be possible to execute an invalid message. If you can finalize an invalid message, you can do a lot of damage. And so the number one invariant about this is that you cannot be allowed to finalize an invalid message. Behind that, there's also an invariant that's basically that users should be able to finalize valid messages, right? If users aren't able to finalize valid messages, that's a liveness issue. And so we want to protect the safety issue and the liveness issue. And then, of course, there are some other invariants, like the fact that this portal should never be allowed to send the same message twice, that you shouldn't be able to manipulate a message, all these sorts of things. This portal is very, very important. This is the heart of sort of message passing, which also is the heart of the safety of the bridging system. Cool. So number one goal is make sure that this portal contract is safe, that the fallback mechanisms that we have described and we have created can keep the portal safe, even if there are issues in the fault dispute game, in the dispute game factory. Can these safety nets keep the system safe? The second important thing is making sure that delayed WETH really ensures that the fault dispute game is not getting bonds that it shouldn't. And part of this depends on functionality in the fault dispute game. Part of this depends on functionality in delayed WETH. But again, this is a safety issue. If the fault dispute game can somehow pull WETH out of the delayed WETH contract before it should be able to, then it could distribute that WETH to the wrong parties, which would be a safety issue, especially because it could be the case that there are many millions of dollars worth of ETH held in bonds between these two contracts. Some important caveats is, I think probably the most important caveat about this whole contest is about the fault dispute game resolution logic. So this contest specifically, we are not covering the fault dispute game resolution logic itself. We are not covering the logic that determines whether or not a given proposal is valid or invalid. That is something that we're going to cover at a later point, but for this specific contest, you can essentially assume that the fault dispute game is allowed to resolve incorrectly. That is, that when you call the resolve function and the resolution state is set, it is allowed to be wrong, and the rest of the system must still be safe. So if you find issues in the resolution logic, we always appreciate reports about issues like that. But for the sake of this specific contest, those issues are not in scope. So that's just an important thing to remember. There are other behaviors about the fault dispute game that are in scope. For instance, there's a field called resolved at, which stores the timestamp at which the fault dispute game resolved. It is important that that field is set once and that it's accurate. If that were not the case, you would be able to bypass the air gap window. So confirming that behavior about the fault dispute game is important. And you can get to that conclusion by looking at the Optimism portal, by looking at the finalize withdrawal function, and understanding that finalize withdrawal does make assumptions about the fault dispute game, but it does not make the assumption that the resolution status is actually correct because of the existence of the air gap window. Okay, that is the very, very high level. That is the main idea behind all of this. I'm going to stop there for a second just to check if there are any questions. I don't know how to pause this so that I don't get the infinite window in a second here. Uh-oh. How do I prevent the infinite window?
It's okay. There are no questions right now. I just checked the YouTube chat.
All right, great. Then I'm going to take a sip of this coffee, and
in case any questions appear, Sven will redirect them to you.
Yeah, there are no questions yet.
Okay, cool. It's also quite early, and people will probably have questions later in Discord. Okay, so we've covered the high level now. I think generally speaking, just to recap, the biggest shift in this whole thing is that we are replacing the L2 output Oracle contract with these fault dispute game contracts that are created by the dispute game factory. And there are certain properties about these different contracts, and specifically about the Optimism portal, that we really, really want to maintain. And those things are the key invariants that we are trying to maintain and trying to assert as part of this contest. So if you can break those big invariants, please tell us. That's very important. Cool.
So we have a couple of questions coming in right now.
Cool.
First one was like, so the L2 output Oracle is gone, and I think it was already answered. Yes, it is gone.
Yes.
Second one would be, is the storage proof provided from the data up to the account proof to the date root?
Okay, so the proof that there's sort of a bit of a protocol quirk here. The proposal that is submitted is not just the state root of the system. It's actually the combination of the state root of the system plus the block number plus the it's essentially the block header, but it also pulls up the storage root of this specific contract on layer 2 called the L2 to L1 message passer. And that's really just done so that we can make the Merkle try proof more efficient on layer 1, so that you don't have to prove first the account try and then the storage try. It just simplifies things. So we pull up the root of the storage, the storage root of this one specific contract called the L2 to L1 message passer contract. So the proof that actually ends up going on chain is only the storage proof for that one specific smart contract. in order to send a message, you have to, on layer 2, trigger a call to this specific smart contract on layer 2, which then puts the message, the hash of the message, into storage, which you can then prove on layer 1.
Cool. Thank you for. I think this answers the question quite in detail. Yeah. Thanks for that.
It is worth noting that the Merkle trie logic is it's been looked at quite a number of times before, and it has not changed as part of these changes. If you want to look at it, you can, but there is also another safety mechanism in place called the withdrawal delay, the 2-step withdrawal delay, that forces users to prove their withdrawal 7 days before they are actually allowed to finalize that withdrawal. And the idea behind that is literally just to address potential issues in the Merkle trie contract, so that if someone were able to forge a proof in the Merkle trie contract, you would have 7 days to detect that forgery and respond to it. So it's probably not super useful to look at the Merkle trie code. I guess you could if you wanted to, but it's much more useful to look at that 7-day withdrawal window and see if that's bypassable. Because if it is, then it doesn't actually help protect against issues in the Merkle trie contract. And I'll show all of that in the code in just a second.
Yeah. So we have a bunch of more questions coming in.
All right, let's keep going.
One of them would be like, can you explain the bisecting process?
Sure. I'm gonna save that for later. Just to sort of reiterate, the bisecting process, though interesting, for this specific contest is not really in scope unless you can figure out how to use that to manipulate other properties that would like sort of break the invariants inside of the Optimism portal. I'll save that one towards the end. I'll basically, for anybody who's just interested in it, I'll go ahead and I'll explain the bisection process and the resolution logic as sort of at the very end.
Yeah. Okay, makes sense. Next question would be, is it users who deposit into the delayed wrapped ETH contract?
So the delayed wrapped ETH contract technically is open for anybody to put funds into, and you should consider that possibility when looking at how you might abuse that contract. But in typical usage, we don't really see a good reason why people would do that, other than to maybe try to exploit the system. Generally speaking, users are not depositing into that contract directly. What happens is that users are sending bonds to the fault dispute game, which then forwards those bonds along to the delayed WETH contract to be held. The reason for that, rather than having users interact with delayed WETH directly, was more of a was that we didn't want to break this abstraction, because in the long term, we want to get rid of the delayed WETH contract. And so we didn't want to have the users really know about the existence of this contract. We wanted it to be hidden in the background. So we have them go through the fault dispute game so that when we eventually get rid of this contract, nothing changes in the rest of the code.
Yeah, cool. Thanks. Okay, then there was some discussion in the chat, and then another question would be regarding the scope. So the only things in scope in the fault game contract are the assumptions used by other components of the protocol, like Optimism Portal 2.
That is correct. So I will go through the Optimism Portal 2 contract and demonstrate examples of how there are assumptions being made about the behavior of the fault dispute game, and then also show how other behaviors would not impact the correct behavior of the Optimism portal. So I'll go through that.
Great. Yeah, I think then we should go on with that now.
Great. Okay. All right. We're going to go switch over. I think we can show my screen again. And then we're going to switch over to my code. Yay. Okay. All right. Can everyone see this correctly? I hope so. If I can just get a verbal confirmation, that would be great.
Yep, we can see the VS Code. Yep.
Great. Okay. So, all right. So what are we looking at? Well, today we are looking at the contracts that we just talked about. Most of the contracts that we're looking at are in this dispute folder inside of Contracts Bedrock, but we're going to start with the most critical contract, which is Optimism Portal 2. So just a note, please don't get confused by this. There is Optimism Portal, and then there's Optimism Portal 2. The reason that both of these exist is because Optimism Portal is the code that's being used today. Because this is not an approved upgrade yet, this has not gone through governance, we have to put the new code next to the existing code. And we, in CI and in things like that, we run both versions. We make sure that both things are working. So eventually we will replace Optimism Portal with Optimism Portal 2. We'll probably change the name of this to Optimism Portal and whatnot. But when you're looking at this code, make sure that you are looking at Optimism Portal 2 and not at Optimism Portal, because you will be looking at the wrong code if you do that. Okay, Optimism Portal 2. So this is a fun contract. We're going to skip some of all these things. There are spacers here. This is just something useful to note. Spacers are just something we use when, because these contracts are upgradable, we just throw them into existing storage slots that we no longer use. You might be familiar with that, but just worth noting, that's what they are. All right, so let's get into it. All right. First thing, when you create the contract, you are connecting the contract to a couple different things. There's the proof maturity delay seconds. This is the delay after you prove your withdrawal that you must wait until you can finalize a withdrawal. And we'll look at that in a second. And then there's dispute game finality delay seconds, which is the air gap window. This is the delay between when a dispute game resolves and when it can actually be used. And then there's the respected game type, which is basically just saying which game implementation are we allowing people to use at this time. All right, so let's get into, we're going past all these things, and let's just get into the meat of the important things in this contract. So the main functions that I suspect you'll be looking at within this contract are prove withdrawal transaction and finalize withdrawal transaction. And then, of course, prove withdrawal transaction calls out to some of these other functions. And so does finalize. So prove withdrawal transaction. What is this? This is the step where users are proving that their withdrawal was actually included in the state of the layer 2. In order to do this, you are providing first a transaction, a withdrawal that you are proving. This is a message that you are proving. You are providing a dispute game index. This is just a pointer to a fault dispute game contract. I'll show you that in a second. There's an output root proof, which is an output root. An output root is the concatenated hash of a couple different elements. And so if you want to talk about the contents of that hash, you need to provide the contents, which we will then hash. And that allows us to just confirm that we are talking about the correct contents of the output root. And then finally, there's the withdrawal proof, which is the Merkle-Try inclusion proof that says this withdrawal was really included in the L2 to L1 message passer contract. Okay. So if we walk through this, let's just kind of go through it line by line. So what we're doing here first is we don't want people to be able to send messages to the portal itself, because we don't want people to be able to cause the portal to trigger its own functions, because, for instance, deposit transaction down here uses the message sender. So we don't want people to be allowed to have the portal call itself. Then what we're doing is we're looking at the dispute game factory, and we are looking at, we are trying to get the game at a specific index, and that's going to tell us the address of the game and the game type. That game has a claim, which should be a proposal about the state of the layer 2. Then we do a number of checks here. So the first thing that we're checking is the game type actually correct? Is this the respected game type? Because there are multiple different game types. There will be different game types over time as these game contracts are updated. And we don't want people to be able to use the wrong implementation. So we check that the game type is correct. Then we look at the output root, the claim, and we verify this proof basically about the contents, this output root contents that we're looking at, which allows us to just check that specifically, I'll get to that in a second, that the storage root, you'll see here, the message passer storage root is actually the storage root that this claim commits to. So once we check the output root proof, we go down here. So we compute a hash of the withdrawal, and we try to see if this withdrawal has already been proven by this particular user yet. There are situations in which we need to be able to do this, because there are situations in which a user might prove a withdrawal against a specific dispute game, and that dispute game becomes invalid. And if that dispute game becomes invalid, either because the dispute game has been blacklisted, or the respected game type has changed, or it was just proven to be invalid, then the user has to be able to reprove that dispute game to the contract so that they can try to withdraw again. So the first thing that we check is you're not allowed to prove a withdrawal against a game that is invalid. Challenger wins is another way of saying this game was invalid. You're not allowed to do that. Then down here, what we do is we check whether, if this condition is true, that basically means this withdrawal has not been proven by the user before. And then we check all these things about the old game, the previous time that this withdrawal was proven. Is the old game invalid? Is the old game blacklisted? Has the game type changed? If any of these things are true, then the user is allowed to reprove the withdrawal. So while I'm here, you'll kind of notice that we're now starting to see where a couple of the assumptions about the fault dispute game start to come in. So you can see this call to status, for instance. This call to status is a call against the fault dispute game contract. If this call reverts, then it would be impossible, for instance, for someone to reprove their withdrawal, at least against this specific game. So that's not good. If this status reverts here, yeah, you can't reprove the withdrawal. If this game type reverts, you can't reprove the withdrawal. Things like that, right? Once we've checked, okay, either this is a brand new proof or the user is just reproving because the game type, the old game was invalid, then we're going to check whether or not this is even a valid withdrawal. So to do that, we compute the storage key for that withdrawal hash, and then we verify a Merkle-Try inclusion proof. If this Merkle-Try inclusion proof checks out, then we say, okay, fine, here you go. You have proven this withdrawal. Great. this and this push here is just a convenience thing for the sake of making off-chain things a bit easier. Great. So that's withdrawal proving. When you prove the withdrawal, you're basically storing the proxy, the default dispute game contract that you proved the withdrawal against, and you're also storing the time at which you proved the withdrawal. Now, cool. That's the first thing there. I'm going to pause for a minute just to see if there are any questions about prove withdrawal transaction. This is the idea. General idea behind this logic here is that you should be able to prove any withdrawal. Please note, though, that in prove withdrawal, in this code path, we are not making any assertions about the validity of the game, except to assert that it is not explicitly invalid. This status could be valid. It could also be in progress. And so it is possible that someone is proving a withdrawal against an invalid proposal. And that's okay, because later on in finalized withdrawal transaction, in what the call to check withdrawal down here, we must assert that the status is actually defender wins, which means that the proposal is valid. Okay. Any questions there before we move on to finalize withdrawal transaction? I can't see the chat, so if there are no questions.
Okay, so there is actually, let me check that. There was some discussion going on in the chat, so to figure out what is the final question we should ask. So there's actually a question directed to you. Is the root claim of a dispute game the same on an output proposal in the old L2 output oracle? The
Yes,
same as in
it is the same. The root claim is the same object, same structure, same contents. Yeah.
Yeah. Okay. Yeah, I think there's no other open question regarding this one so far.
Got it. And we'll be in Discord after this to be able to answer any other questions that people might have. So if you have other questions, don't feel stressed about if they don't get answered during this. Cool. Okay. So proving is step one. The reason, again, that we have separated proving from finalization is explicitly just to make sure that we don't have errors in this kind of logic here. This sort of thing has been the source of bridge bugs in the past, right? If you look at historical bridge bugs, there are a number of them where proof verification, try verification have been the source of the bugs. And so by separating proving from finalization and enforcing an error, like a period of time, a delay between those two actions, it's much harder to exploit a bug in the proving process because there's always time to catch that bug and alert and come in and pause the system and have the security council essentially deal with the issue. So like we said, the first thing is proving. The second thing is finalization. So just for some quick context, it used to be that you could only have one proof for a given withdrawal hash at a time. So this mapping was just this part, and it didn't also key by another value. And the problem with that was with this new mechanism, it was possible to block people from proving their withdrawals. So we made it so that you can have multiple proofs for a given withdrawal pending at the same time. But and so this is why you have this finalized with this sort of legacy interface here, and now it's also keyed by the address that actually submitted the proof. So you insert that as the second parameter. Typically, it's going to be the person calling the finalization transaction. So this is a convenience thing here. But in the case that the proof was submitted by somebody else, you could just add this to your function call and you'll be okay. Great. So let's go through finalization. What is going on? So first things first, we have this check here that basically just says, make sure that the L2 sender is this default L2 sender, which is basically just a reentrancy guard at this point. The next thing here is we compute the withdrawal hash and we execute a bunch of checks. So let's look at the checks that we are going to execute. All right, so we're going to pull in the withdrawal proof, right? And again, it's keyed by withdrawal hash and proof submitter. The first thing we're going to do is we're going to make sure that the dispute game proxy that was used as part of this withdrawal proof has not been blacklisted, right? Blacklisting is something that the Guardian, the Security Council can do in the case where a specific dispute game proxy resolves incorrectly. The second thing that we do is just a sanity check, which is make sure that this thing has actually been proven. Well, I mean, if it hasn't actually been proven, most of these other things are going to fail. So maybe this isn't super necessary anymore. But if the timestamp is 0, then it hasn't actually been proven. So we need to do that check. Now, next thing here is we're going to confirm that the dispute game proxy was created after the withdrawal was proven. This is just a sanity check. This isn't super important, but it would be weird if somehow the dispute game proxy were created before the withdrawal were proven. That's a weird case, but it shouldn't really be possible. But this is just a check we're doing. The next thing is that we are confirming that the withdrawal timestamp is at least proof maturity delay seconds ago, right? So this is enforcing that delay period between when the withdrawal is proven and when the withdrawal can be finalized, right? So if you can manipulate this timestamp somehow, that would be a problem. Now, then we're going in here and we're checking the status of the game. Did it resolve to defender wins? If it resolved to defender wins, great. We can use this to finalize a withdrawal. If it did not resolve to defender wins, no good. We can't use that. Then we're continuing to do validation checks. We're checking whether the game is the respected game type at this moment. And then we're also going to check whether the game was created after the respected game type was last updated. And so the reason for this is we don't want people to be able to play games before the respected game type was changed, when maybe no one was looking at those games, and then use those games to finalize a withdrawal. That would be very bad. So we want to make sure that only after people started caring about those games were those games actually played. Then, sort of almost last but not least, but is we have an additional check here, which is the air gap window, and we're checking that the game resolved at least dispute game finality delay seconds ago, right? The point of this is after the game resolves, we need to be able to have a certain amount of delay time where off-chain systems can look at the resolution of this game, determine whether the resolution is correct or not, and propose and potentially block the dispute game if necessary. And then finally, of course, we check that this withdrawal has not yet been finalized. I'll get back to this function in a second because there's some important stuff in here. But for the moment, I'm going to switch over back just to this function to complete what goes on. After we check the withdrawal, we're going to go ahead and check that we're going to set the withdrawal as finalized so it can't be replayed. We're going to set the L2 sender. We're going to make an external call. We're going to set the L2 sender back to the default value, emit an event, and you don't really have to worry about this part right here, but that's just for gas estimation. So cool. That's the general idea. We are checking. We're basically saying we can't re-enter this function. Then we are checking the withdrawal for all these conditions. Then we're saying, okay, this withdrawal should be finalized. Then we're actually making the call, the external call. And then we are sort of resetting back the reentrancy flag, and we're done. To go over the check withdrawal function, because this is sort of important. Again, the high level thing, I talked explicitly about the actual checks that are going on here, but the high level thing is we want to make sure that first, this proof is valid, right? Is this really a valid proof? Second, is this proof against a valid game, right? Is it a game that has actually resolved correctly? And is it a game that is the current game type? All these things. Also, we are checking our safety mechanisms, right? We're checking the blacklist. Has this game been blacklisted? Has the respected game type been changed to make it so that this game can no longer be used? Was this game created after the respected game type changed? And finally, are we still in this air gap window or not? Now, this function really highlights the sort of the behaviors of the fault dispute game that are really important to the proper functionality of the Optimism portal. So if we start with created at, right? Let's just start with the reverting case. If created at reverts, then this function is uncallable, right? You can't actually call check withdrawal. So this function must not be allowed to revert. Otherwise, someone would potentially be able to, or potentially not be able to finalize a withdrawal that is actually valid. Additionally, if created at is incorrect, right? If someone is able to manipulate created at, if it does not accurately reflect the time at which the game was really created, then this check is meaningless, right? This check is meaningless. So none of these things matter, right? So if you can manipulate that value, you have some problems. Similarly, right, if you can manipulate game type, then this respected game type check doesn't matter. Or if it reverts, then you have a liveness issue. Very critically, if you can manipulate resolved at, if resolved at can ever be put into a state where it does not accurately reflect the time at which the game resolved, the time at which the resolve function was called, then you could completely bypass this air gap window. So even though the resolution logic itself is not part of the scope, the behavior of some of these functions is, because if you can break the behavior of some of these functions, then you have an issue. The last thing I would mention here is status is sort of important. The invariant that needs to hold about status is just that the status can go from in progress to either defender wins or challenger wins, and that's it. If the status is in defender wins, it should never be able to switch to challenger wins or vice versa, right? So this if you look at the the state machine for status, it starts at in progress and it either goes to defender wins or challenger wins and stays there, and it could never switch between the two. If that property holds true, then it doesn't really matter what the status ends up being, as long as this air gap window resolves, as long as this air gap window holds. Because if the status is wrong, right, if it's set incorrectly, and the air gap window still holds, then it's possible for off-chain monitoring to detect the fact that the status is wrong, to then blacklist that specific game and prevent it from being used in a withdrawal. And so that's what we basically say, that the result of resolution doesn't matter, right? It doesn't really matter whether or not the status is accurate or not, whether or not it's really defender wins or challenger wins, as long as it is set during resolution, right? It can't be set later. Like at the same time that resolved at is set, status must be set once, and it must not change ever afterwards. So that's just to sort of illustrate the ways in which the correctness of this portal does depend on some properties of the fault dispute game, but does not depend on all of the properties of the fault dispute game. All right, going to take a quick break there. Any questions? Oh, sorry, I forgot the infinite window. All right, any questions there?
Yeah, there was one question which was already answered in the chat about that there will be multiple games at a given point of time, and we already got the answer in the chat that they are. Yes, that's the case, and right now on Sepolia there are many to see already.
Yes,
yeah.
so there can be multiple games at the same time. You can also have multiple games that have competing claims about the same block, for instance. So it's not just multiple independent games, but even multiple games that are competing about the same claim.
Cool.
Yeah. So this is Optimism Portal 2. This is really the heart and soul of the system. If you can figure out how to bypass these air gap windows, if you can figure out how to bypass these fallback mechanisms, that's really critical, right? If you can figure out how to re-enter these contracts so that you can execute the same message more than once, that's really critical. It's that sort of thing that these checks are trying to prevent. And any time where this thing calls out to the fault dispute game or the dispute game factory, you really want to look at those contracts and make sure that these assumptions about the behavior hold, right? Is it the case that status can only be set once and that it can only be set when the resolve function is called? Is it the case that resolved at can only be set once and it can only be set when the resolve function is called, right? These things are very important. So then we can quickly look at the dispute contracts just to look at it. The dispute game factory is a pretty small contract, and it basically just creates fault dispute game contracts. So of the things to check within the dispute game factory is just making sure that the things that are getting created, these fault dispute game contracts, actually have the right code in them, right? I mean, it's great if we can confirm the correctness of the fault dispute game contract, but if the dispute game factory is creating arbitrary code, is creating the wrong code, then we have a problem. So confirming that the dispute game contract is creating the right code is very important. That there's not a way to manipulate that code some way is very important. Confirming things like, is the game type correct? Is it actually sending the right game type to the fault dispute game contract, right? Anything that could allow a user to manipulate the values that are queried in the Optimism portal are those are very important things. And then you have some permissioned functions here, which should be only owner, and that's I mean, it's pretty straightforward, but confirm that that's correct. So the dispute game factory creates these dispute game contracts, the fault dispute game contracts. Now, the fault dispute game contract is quite a complex contract, which is why we are choosing to try to analyze these contracts in the way that we are. There's all these different functions here. Step, right? That's a big function. Move, attack, defend, all these different things. And I can talk about that later. But we, like we said, the invariants that we care about are generally these things in the Optimism portal, right? So things like, great, resolved at can be called during the resolve process, but it should only be able to be called once, and this value should not be able to change in any way, and status should not be able to change after it's been called. Those are, those are the sort of important things. Generally, resolve claim, this is a very complicated function. There's a lot going on here. Move is complicated, but again, unless you can figure out how to exploit some of the other behaviors that the Optimism portal relies on, the actual result of resolve claim, like the actual resolution, the value that the status takes on, doesn't matter except in the ways that we described earlier. Cool. So there's a lot of different things. I think the very last thing to talk about is bonding. So the important thing here is, I think besides the invariants that we talked about in the Optimism portal, the most important invariant in the fault dispute game is that if you don't deserve a bond, you shouldn't be able to get one. And we know that it's possible for resolve claim, right? So resolve claim, you'll see, is the function that calls this other function called distribute bond. Distribute bond gives a recipient a credit to be able to withdraw some WETH from the contract. We know that it's possible that resolve claim could be wrong. So we know that it's possible that a recipient could be given a credit that it doesn't actually deserve. And so for that reason, that's why we introduced the idea of delayed WETH. And delayed WETH is basically this thing that forces the contract to wait when claiming a credit. So claim credit, right? This is its internal accounting, but when it does its internal accounting, it actually has to withdraw from the delayed WETH contract, and that delayed WETH contract has a delay on withdrawals here that basically enforces that that there is a withdrawal delay every time that you want to get funds out. In order to use delayed WETH, basically what you do is you say, hey, I'm going to unlock this amount of WETH on behalf of this user. So I'm going to create a withdrawal request for that. I'm going to update the timestamp at which that withdrawal request was created, and I'm going to add that to the total withdrawals that I have allowed for that user. And then I later am going to finalize a withdrawal for that user by basically just checking, okay, we've already requested that amount. The timestamp is not 0, and at least the delay seconds have passed since I initiated that withdrawal. That's the basic mechanism here. This is noted in the handbook, but you'll probably notice that there's kind of nothing stopping you from just putting in whatever address you want here as the recipient. It kind of doesn't matter. For most users, this accounting is sort of what I call soft accounting. Just because you specify a specific user doesn't mean that those funds actually have to go to that user. And again, the reason for this was to not have the delayed WETH contract leak, not have the abstraction leak, and make it so that users had to be aware of this specific contract. But so it essentially just means that the only important invariant here is that the address that goes into claim recipient ends up being the address that goes into withdraw. Because if that invariant holds, right, if you're not able to manipulate this parameter here, then it is the case that this accounting is sort of hard accounting in the sense that the funds will go to this specific recipient address. If you're able to get the fault dispute game to put something random into that, that's not good. If you're able to get the fault dispute game to call this function when you shouldn't be able to call this function, that's not good. I think that's about it. And then, of course, there's just verifying the functionality of the fallbacks within the delayed WETH contract. The two fallbacks being recover, which essentially allows the Security Council to take ETH out of the contract in case it needs to, in case there's a massive issue, and hold, which basically just forcibly gives an approval, which can be combined with, if you combine that into a transfer from within the same transaction, then you can approve and transfer from, and essentially just pull ETH out of a specific fault dispute game, just to hold on to it until you can figure out how to resolve issues with the resolution.
Yeah,
great.
So we have one question in the chat, which is, in case of a wrong game result, the admin will call the admin only withdraw function to withdraw all the wrapped ETH, leaving no more for the user to claim their bond. Is that correct?
So it sort of depends on how the game resolves incorrectly, but probably what would happen is that if a game resolves incorrectly and distributes credits to the wrong parties, right? It does not distribute credits to the parties that it should have distributed credits to. The admin would recover the ETH, or sorry, not recover it, but hold the ETH from that specific dispute game. And it'll essentially, like, it'll figure out how to distribute those bonds back to users. There's a number of different options. You can either distribute the bonds as if the game had resolved correctly. You could just give the bonds back to the original users who put the bonds in. I think that the exact mechanism for what you do with that is up to the Security Council, up to the people who are thinking about this. And it depends on the context of what went wrong in the game. But the general idea is that, yes, it will, within this delay period, take the WETH away from the fault dispute game, hold on to it, and figure out what the right way is to redistribute that WETH.
Cool, thanks.
Cool. Any other questions?
Not so far.
Cool. On this specific this specific thing, I'll sort of just give you an intuition for like what could, how could a fault dispute game go wrong with this delayed WETH contract? I mean, let's say that even if the withdrawal, like, okay, I wait for the withdrawal delay, but then somehow the fault dispute game withdraws those funds and then sends them to the wrong person, right? They withdraw, they put the right person into this address here, but then they actually take the funds that they withdrew and they send it to the wrong person. That would be an issue, right? So that's that would be a valid report if you could demonstrate that were possible. Additionally, another potential issue is if you can force the fault dispute game to somehow call unlock early, right? If you can force it to call unlock way ahead of time or whatever, you can make this timestamp start ticking, long in the past, so that by the time that it's actually time to start withdrawing bonds, then you don't have any delay, and so the delay doesn't matter. And so we want to make sure that unlock can only really be called during the resolution process, during the claim resolution process, so that there's not a way for someone to just instantly withdraw something that they shouldn't be able to withdraw because they called unlock far in the past. And then, of course, make sure that only the owner can actually do these recovery actions. Look at WETH 98, which is just a version of WETH 9 for Solidity 8, which allowed us to just make delayed WETH. This should be pretty straightforward, but worth looking into anyway. Yeah, I think that's really the majority of it. I don't think there's much else that's basically it. Top priority is the Optimism portal safe? Can the safety mechanisms be bypassed or something like that? That's the number one priority. That's what matters more than anything. Second priority is looking at the delayed WETH contract and making sure that bonds can't be stolen. And then after that, I don't know, right? I mean, we'll talk about we can maybe talk a little bit about the fault dispute game resolution logic. But again, whether or not the game resolves correctly is not a part of the scope for this contest. Cool.
Great. I guess we should address any questions that will appear and have at the end a short Q&A. And yeah.
Yeah, so now is the time. If you still have any questions, write it in the chat, and then we will wait a few minutes to see if they are coming in.
Otherwise, Kelvin is going to be in the Discord. It's going to be active throughout this week, and you are able to ask him any questions you want.
Yep. Yeah, I'll be in the Discord pretty much all the time throughout the whole contest. I'll also be hosting office hours when I have availability. So I'll just try to announce that ahead of time. I'll just make an open meeting. Anyone can join if you have questions. Also, feel free to join anonymously and just put questions in the meeting chat or whatever. But I'll be there, and you can ask me whatever live rather than waiting for responses in Discord.
Yeah, there were no questions coming in so far, I think.
Yeah, in that case, we'll have to thank Kelvin. I'm sure this was exhausting on his end, but thank you very much, Kelvin, for giving this overview to all the security researchers. I'm sure it's going to be very helpful for everybody to quickly understand what's happening and what are those areas they should focus on most. And hello to everybody that is watching this in the recording, and hope everybody has a great day. And yeah, I think we can end it here.
Cool. Yeah, I would say just as a final note, if you look at the Q&A, it has a lot of the details. At the end of the Q&A, there's also a link to a big handbook that has a bunch of information, basically everything I talked about today in written form, diagrams, everything. So feel free to look at that, and then I'll be in Discord for questions. So cool, that's it.
Perfect.
That's it.
Thanks a lot.
Thanks,
Thank you.
everybody. Bye-bye.
See ya.